Alright, welcome back to video 2. We're still on unit number 2, forces. And this video is going to work a little bit differently. So this one has a lot more to do with problem-based ideas rather than last video, which was a lot more foundational. So you can see, like, the examples from yesterday used a lot more just kind of arrows and bland boxes, I might add. Whereas in this one, now we have upgraded boxes, gradients, and color-coded forces, and those will be useful when we're talking about the forces specifically in this video. And then at the end of the video, I'll also have some problems for you to do. You can pause, and then I'll put some solutions up right afterwards. Alright, so this video we're going to learn about the force of gravity, or gravitational force, whichever one you like, normal force, net force equations, inclined planes, and we're going to do some mini lesson here on splitting vectors into its components. Let's get started. Alright, number 1, force of gravity. And, most people know about this one. It's not exactly an unheard of force. It's very common, and it has to do with everything, basically. Everything on the Earth has some force of gravity pulling it towards the center of the Earth. You may notice that from the video from yesterday, right, it looks a lot like this equation right here. The only difference is this is the force of gravity, where we have mass times the gravitational acceleration, and then just kind of a generic force is mass times acceleration. So this is a little more specific, where it's the acceleration due to gravity. And everything has a gravitational force, including a 10-kilogram box. Even the Earth feels some gravitational force back at you, actually. Everything on Earth has a little bit of gravity pulling it down towards the center of the Earth. And something to point out is that in free body diagrams, every gravitational force will always be pulling down. So even though technically it's towards the center of Earth, in free body diagrams, FBDs, they will always be pointing down. I will actually be using these purple arrows to represent gravitational force for reasons that might become clear when we start working with inclined planes. Anyways, 10-kilogram box pulling down with the force of gravity just because it has 10 kilograms, right? It's the only reason it has this force, and we can point out that force with this equation, right? We have force of gravity in newtons equals 10 kilograms times gravity, which is measured in meters per second squared. And again, that's the acceleration due to gravity, which makes it ties it closer to this equation right here. But what is g? Like, how do you know what this number is, right? It's some acceleration. Well, it depends on where you are, actually. The equator is a little bit farther from the center of the Earth, so gravity is actually a little bit lower near the equator. And you can lose pounds quick by moving to the equator. Only about 0.03% of your mass, or maybe 0.3. It's basically nothing. It won't actually affect you, and it actually depends on what kind of problem you're doing. So a lot of standardization problems will use like very specific values for gravity. The closest one I found was 9.807 here, but also we use a lot like 9.81 or 9.8. I'll be using 9.8 just because it's 10 is used for some conceptual examples that you might find in other videos. Those just kind of set up like the ground foundation. So like if I plugged in 10 here, it would make the force 100 newtons, which is just a little easier to see rather than times 9.8. But also, these are other gravities. This is for Jupiter and the moon, actually. So it's like, you can use Earth's gravity, but the force of gravity is always going to be with this box no matter where it is. So you can have, you know, it might weigh 98 newtons on Earth or 16.2 newtons on the moon or 247.9 newtons on Jupiter, right? It has all these different weights even though it's still just this 10 kilogram box. So sometimes it's more useful just to say G. 10 times G newtons is like universal, right? So this G you can substitute in wherever you are. I might take a trip to the moon and I'll be able to write my weights in 10G even though I'm not with the Earth's gravitational pull. And same thing with this 15 kilograms, right? This arrow, this vector, this force, right? It's all the same thing. It's a little bit bigger because it's a lot more mass. And again, this is 15 times G, or again, 9.8 meters per second squared. We get 147 newtons. But what if I push it a little bit this way? And this is, barely anything, just a little bit this way. I'm just kind of pushing it. Well, then we can move it around just like yesterday and find the net force. So this is, the net force is still going down. So this force wasn't enough to pull it away from gravity, right? It's still being pulled down by gravity, although it's moving left a little bit now. And you may notice this little FA. That's another shorthand for F. In this case, it's the applied force, just because I was pushing it this way. It's just kind of a generic, like, something that's happening, but not necessarily gravity or some of the other forces we'll be talking about today. Including number 2, the normal force. Now, some people like to say that this is the force normal just because it's Fn. You can say Fn, but please, it's the normal force. It drives me crazy when people say force normal. All right, so we have 10 kilograms, and we already talked about 10 times G, 98 newtons. But what's happening, right? Now it's on some surface. This could be the ground or a table. But now we're looking at, well, if it's on the ground, it's not moving. It's not accelerating. So the net force is 0. How is there a net force of 0 if it's being pulled down by gravity with 98 newtons? Well, this ground is actually pushing back up at the object with a certain amount of force, and it's called the normal force. And particularly, like, you got to kind of pay close attention to this. It's the ground is pushing back at it perpendicular to itself. So, in this case, the ground is flat. So gravity is straight down, normal force is straight up, and it's all good. But when you tilt it a little bit, and we'll get into this later, but when you tilt it, it'll be perpendicular to the surface because the surface is pushing back up at the object. And this leads us to our first mini lesson. So, what I want to answer is, okay, so we have this, the net force is 0 newtons, but how do we find the number for the normal force if we have gravity? So how do we find what the normal force is if we have mass times acceleration with 0 newtons, right? And we'll actually start with this example real quick, just kind of as a generic, and that kind of happened quickly, but just kind of move those forces around. We did this yesterday where the sum of all the forces leads right back in the middle. So the net force is 0, and mass times acceleration is 0 because all the forces lead back to the center of mass. But another thing to do is the net force, or the sum of the forces equation, right? And this is where you literally write out, these are all of the forces that are being acted upon this object, so you can write them all out. So the net force is if you add them all together. And that's with this little sigma notation. We already talked about it, right? So we can say that, you know, if the net force is 0, MA is 0, and this sum is 0. And we'll also do this with the y and x components. And this is, it seems redundant now, but it'll be helpful in just a second. Or in just a minute, actually. So if we start with the y components, right? If we have the y component for f1, y component for f3, f2, it all equals 0, right? If we go down f1 y amount, and then we go up, and this is why it's negative and positives, right? We go down this amount, and then go up, like we said yesterday, a little more than halfway, and then that final distance is covered. And if you rearrange this a little bit, right, you add f1y, you can kind of restate what we just said, right? If you go f3y distance and f2y distance, that is the same thing as if you just go the f1y distance, which is exactly what we say here, right? f2y plus f3y is f1y. And we can do the same thing with the x. If we just go f1x plus f3x plus f2x, we'll get back at the start with 0. F3 is the only one that goes left, and left is negative here, just because I decided so, right? With positive and negative directions, it's really about what you choose. And in this case, I'm choosing that left is negative because I feel like it. And that simplified a lot for two reasons. One, you can add over the f3x, like we did with the negative y. But also, f1x doesn't show up here because there is no x component for this. It just goes straight down. It doesn't go side to side. And this you might see as, okay, well, the distance left that f3 goes is the same distance that f2 goes back to the right, which checks out, right? And we can use this sum equation back in this example, where we have the normal force going up and the force of gravity coming down to equal 0. Rearrange this real quick, and we get Fn equals Fg. And it only equals that because this surface is flat, which is a very important detail that we'll get to like very quickly. But in this case, Fn equals Fg equals 98 newtons, which makes sense, right? If 98 newtons goes down for gravity, then the table or the floor or whatever is pushing 98 newtons back so that it doesn't move at all. It doesn't accelerate at all. And another way to kind of lead into these inclined planes is to think of this floor or table or whatever as an inclined plane with a slope of 0 degrees or an angle of 0 degrees, which is a very weird way of stating like a table or the ground, but it's more confusing just a little bit when we start talking about angles of like 40 degrees and, you know, basically anything bigger than 0, really. So this crate is an unknown mass. I'll say it's bigger than the other one. And it also has the force of gravity. And again, I'll be using this purple for something very clear in just a second. And then the normal force. And again, what I was just saying was the normal force is perpendicular to the surface. Because in math, the normal force is actually, like, normal means perpendicular in math. So anytime you see a normal force or a normal line, you'll always start to think perpendicular. So in this case, perpendicular is straight up. In this case, perpendicular is 40 degrees this way. And you'll notice it's a little bit shorter than the force of gravity. Why? Because it only cancels out with the forces in this direction. but there are no other forces in this direction. Okay, but it might seem a little confusing, like what is it canceling out with? Well, mini lesson. Sorry to kind of get off track for a little bit, but this will be really important. So we start with some vector that we have in the xy plane, and we're pretty good with splitting things up into x and y components. However, how do we find these x and y values? Well, we can use trigonometry, and this is just a very brief trigonometry recap. I'm not really going into it this time. However, right, the cosine of this angle is the adjacent over hypotenuse, x over green. So to find x, we just multiply by green for both sides, right? We multiply by the hypotenuse to get green times the cosine of theta is x. And same with sine. Sine is opposite over adjacent, or opposite over hypotenuse, excuse me. And so when you multiply by the hypotenuse, you get green times sine theta is y. But I can also choose a different set of units. Instead of saying x and y, I can choose this new x and new y that aren't just left and right, up and down. And this, it seems a little odd to do this, but the math works out the same way. So in this case, you know, theta is a little smaller, so, but it still works the same way. Theta is adjacent over green, right? So multiply by green, and we get green times cosine theta is new x, and green times sine theta is new y. So it's not 3, 2 anymore. It's some distance and some distance, right? New x and new y. But why on earth would I change what x and y are? Well, I would change it so that I can have some force that this will cancel out with. Right? Right now, force of gravity is in the x and y direction. This, the normal force, is what's acting weird. But I can split it up like this, so that now, right, instead of having all y and 0x, I have some new y and some new x. And you know, this helps me kind of visualize it, where now the force of gravity is what's weird, right? This is going all over the place. But now we can more clearly say that this red is the y direction and this blue is the x direction, right? The blue is down the slope. And now it doesn't look like a slope, so it's a little easier to see. And actually, this is why I chose purple. I was gonna do this blue color actually for gravity, but I figured if we're gonna be splitting it up, we might as well do, you know, red plus blue equals purple. Well, and you could also say if these two forces were separate forces, you could say that, you know, quote unquote net force of these two, you take red plus blue equals purple. So then it all checks out, right? Force of gravity is still happening, but we just claim in this example that they're going to be two different forces. Okay? And first, right, we can figure this out by just saying, okay, hypotenuse times the cosine of the angle, and it's cosine because it's adjacent to the angle. Okay, this angle is what's 40 degrees, right? It's the smaller angle of the two. And you can see, right, it's the cosine is adjacent over hypotenuse. So that kind of trips people up, because usually in the xy plane, we're looking at the angles like this. So then cosine is the x direction. But in this case, cosine is actually the y. And you just kind of have to think about it, because cosine is always the adjacent side, right? So if you have an angle over here, then cosine will be the x, right? That's just kind of a thing to watch out for when you're doing problems on your own. Right. And then we move on to the x direction, which in this case is sine, again because it's the opposite side times the hypotenuse. Checks out. And also, now we know what force this normal force balances out with. It balances out with the force of gravity y component, or, the quote-unquote new y, right? Because before it was all y direction, but now, because the normal force has to be perpendicular to the surface, we can say that now this part of the force of gravity is also perpendicular to the surface. So now this can balance out with the normal force. So like this, right? Like we just said, the normal force balances out with the y portion, and then the x portion is what's left. So now the net force is straight this way, right? There's no y direction, which makes sense, right? If you have an object on a table sliding down it, maybe it's not going to accelerate into the table or off the table. It's just going to accelerate down the table, which makes sense. All right. That actually concludes this video, and this is actually take 2, and that just went way faster than the first take. The first take was like 40 minutes. Oh my goodness. All right. So I'm very glad to say we covered force of gravity, normal force, inclined planes, and what to do with them, particularly in free body diagrams, right? Normal force is always perpendicular, even when it's an inclined plane. When it is, right, you split it up into new x and y components specifically to have the normal force cancel out with something, right? And then we have the force of gravity, which was pretty easy. And this is where we have the problems. If hopefully seen them already. Number 1, draw a free body diagram and find the force of gravity if you have a 23 kilogram object. It's a little random number, but just whatever. Problem 2, draw a free body diagram and find g if it's a 50 kilogram object that has a force of gravity of 365 newtons. And this is not like you're finding g like the Earth gravity. This is just some random planet that doesn't exist, right? It's just you just kind of rearrange this equation to find g. Number 3, we're using normal force and gravity, trying to find free body diagram of a 25 kilogram object on a table under rest, right? It's not accelerating anywhere, so that'll be where the net force is 0. Something to look out for, okay? Problem number 4, this is the tricky one. The inclined planes have a lot more work. It'll be the free body diagram. We're going to split the force of gravity and then find all the forces, and that's just the same thing as this. So don't get caught up in the language. I just kind of slap this together. But 25 kilogram object, so you can use the same force of gravity as you found in number 3, but it's on an inclined plane with 30 degrees. So I'll let you pause, work on those for a minute, and then I'll put up my solutions. All right, so now this is number 1. This one's pretty easy, right? You just have a box, 23 kilograms, force of gravity is 23 times g, which in this case, like I said, I'm using 9.8, so 225.4. Next one. All right, free body diagram, and this one you can do it a couple different ways. So I just drew this. This is all you need, and you can just plug in what you have, right? You have 365 newtons and 50 kilograms, and then just divide by the 50 kilograms to get 7.3. Or you can use this triangle from yesterday where you cover up g, and now you have force of gravity over mass equals g. Okay, same, this is the force of g, this is the mass. This is exactly what we did. But yeah, that's the answer to that one. This one, a little trickier, and excuse the the side part a little bit. So yeah, so we have 25 kilograms. Gravity, you just multiply it like we already did, 245 newtons. And, you know, on a flat table, it's pretty easy to see that normal force will just be 245 as well. But if you really want to show your work, it's not accelerating, we set at rest. So the net force is 0. The sum of the forces, right? You add force of gravity over normal force equals force of gravity. You're all good. This one, I had to use a lot more on my board. That's why it's a little narrower. And sorry for the red. I had to throw that one out. So this one, right? We just found the force of gravity, 245 newtons. And that's the one that's straight down. But to find the y and the x direction, you just multiply by cosine of 30, sine of 30, and I rewrote these equations, right? Cosine of 30 is y over fg, x over fg. Just to kind of show your work right, you multiply by fg, which is 245. Yeah, so the y direction is 212, and that's what the normal force is, right? The normal force equals fgy. So that'll be 212. And then FGX, or which will also end up being the net force, right, is 122.5. That's about it. All right, thank you for watching. Hope you enjoyed, and I'll see you in the next one.